Good morning, everyone, and thank you for registering for this Up to Speed webinar. I'd like to extend a warm welcome to those joining us from HS2, Network Rail, TfL and National Highways. It's great to have you all today and I hope you enjoy this presentation. Today we're joined by Giuseppe Russo and Dimitris Kaltakis, who are going to be talking to us about piloting 4G and 5G for train control and future urban rail applications on Helsinki Metro. There will be a Q&A session at the end, so if you do have any questions, please put them in the chat or use the Q&A tab at the top of the screen, and we'll get back to them. Over to you guys.
Thank you, Kaylee, and good morning, everybody, and thank you for registering and taking time to listening to this webinar that we are presenting. I'm presenting with my colleague and friends, Dimitris Kaltakis. We have been working on this pilot since more than a year now, and we are very passionate about it. Right, so we're going to present the 4G and 5G pilot for train control future urban rail application we've done in Helsinki. A bit of background about the Helsinki Metro. So Helsinki Metro is the metro is servicing Helsinki, including in the eastern side of Helsinki, the Espoo city, and is basically a line that is consists of two lines, M1, M2. And the total length of the metro is approximately 42 kilometers. It includes 30 stations and two depots, Royal Pelto depot that is in the core metro and the Summerworry depot that is underground on the left side of the picture at the bottom. So this is as 30 stations, of 21 of which are basically located underground and the remaining are above ground. So in terms of train fleet generation, the current fleeting has three generation M100, M200, M300, and the two M100, 200 will be soon retired and will be replaced by M400 series that are going to be introduced as part of the METCA capacity program. So let's talk about the METCA capacity program. So basically, there are a number of assets systems on this metro system that are approaching the end of the life cycle, including the existing train protection system. Therefore, there is a need to replace because they are not the reliability start to go down. And there is also requirements to increase the capacity for the entire metro system, because been made some study in the past years where they can see in the next decade, basically the metro will be at the capacity, and therefore there's a need to increase the capacity of the transportation in the Helsinki area. So the METCA capacity program is a program has been coordinated between Helsinki City Transport, that is the company that is operating the metro on behalf of HSL, that is the Helsinki Regulator Transport Authority. And the plan is to increase the capacity for circa 25%, introducing reducing the headways to 120 seconds from the existing 150 to 100 seconds, depending on which section of the line. And the idea is to introduce the semi-automatic train operation GOA2 with the introduction of the M400 series of cars that I've mentioned. Although there is an aspiration also in the future to achieve 100 seconds headways with the GOA4. As I said, this picture now is going to show you a bit of like just an overview of the architecture there, where the new train control system that is going to be a more modern based type of solution and more cost effective is going to replace the existing train protection system. So the new ATC is going to interface with the existing computer-based interlocking and automatic train supervision, which will be applied as part of the METCA program as well. And because the new ATC system is a new is going to be a packet-based type of data transmission, there is a need to build a new radio network that will enable the transmission of data between the train and the wayside system. Right. So why we have done this this pilot, this cellular radio network pilot? We have done this pilot to deploy 4G and 5G communication system and test the suitability for transmission of train control data, as well as data from other metro systems. As I said, primarily the objective was to test the suitability for automatic train control, transmission data, but also we want to test mission critical voice over IP. We want to test live train CCTV for potentially GOA4, that is the future aspiration of the metro metrical capacity. But also there are a lot of there are also a number of existing onboard applications that are listed here on the left side, including a CCTV system, train diagnostics, RFID, passenger counting, train network management, train commercial display, and the public Wi-Fi. All is already existing that we also want to test the possibility to migrate those services over the new radio system that if it's going to be cellular based. And of course, the WSP has played a very strategic role in this pilot, being a strategic advisor for the client, Helsinki City Transport. We have acted as design authority, defining state strategy and providing also helping the client to select the testing provider. But also we acted as technical assurance and acceptance authority on behalf of the client. So now let's talk about a bit more about the deployment. So as I said, the metro has two depots, and the depot that was selected for the deployment of the pilot has been Royal Pelto, that is the old maintenance and depot, which include also a test track that is 1,400 meters long in length. And this depot was selected because it's offering is a good replication of the Helsinki metro environment in terms of open track and the tunnel combination that would allow us to test different conditions in terms of radio condition that we want really to test. So this 1,400 meter of track include 800 meter of open track with multiple roads connected to the depot hall, but we have also 600 meters of tunnel with 200 meters which are in a dual track. In terms of technology we deployed basically two core networks, 4G core with private APN and 5G core. And in terms of coverage, we deployed the public 4G and the public 5G non-standalone at 3,500 megahertz time division multiplexing. And as a private 4G and private 5G standalone, we deployed private frequency 2,300 TDD. In terms of train installation, we installed 3 industrial file routers. 2 were for the private network, and 1 was for the public network. For the public router was connected to 4 antennas installed on top of the train in a 4x4 MIMO configuration, whereas the 2 private router were connected to, each of them were connected to undercarriage antennas installed on the right and left side of the train in a 1x2 SIMO configuration. Now, this is giving a bit of understanding about how we deployed the radio units there for serving those 2 different networks. So for the private 2,300 megahertz network, we installed the leading cables all the way through from the tunnel in the open section, and we had 4 radio unit location number 1, 4, 6, and 7 servicing the leading cables, and also we had the 2 macro antenna 0.8 and 9 in the slides that we deployed to test also lower scenario between macro and the leading cables. For the public 3,500 megahertz, we use, of course, one of the mobile operators in Finland that has already, radio coverage in the area as part of the macro cellular, public cellular. But we also created an infill field coverage in the tunnel because there was no coverage in there, creating 5 remote radio unit location from 1 to 5 position there as back-to-back antenna installed at 1.5 meter from the truck level, pointing, to cover the entire section of the tunnel. Now, let's talk about a bit the testing scope and KPIs. Of course, the testing scope was to measure all the desirable performance indicator that are shown in this table that can inform the suitability of the network to support existing and the future applications. But also we want to measure the performance of the radio environment and confirm the suitability of the antenna and the radiating cable specification location to inform future deployment. But also, we want to confirm the functionality of the existing onboard system over the cellular network if in the future the client would like to migrate over this new radio network. Of course, this table has been of performance indicator has been developed by WSP, has been agreed with the client at CDC City Transport, but has been derived, of course, from existing urban and other metro system requirements documentation and developed by other programs like Shift to Rail, and also from engagement that has been derived engaging with signaling supply, industry supply, and also, of course, coming from WSP expertise in this field. Now, this is perhaps is a little bit difficult to read, but this is like the logical architecture of what we deployed actually by the pilot, where you can see the 2 different areas, the bottom and the top in the pink color, are representing the application layer that has been simulated data stream injected the signal, the data, and the green part, of course, is the radio network that was transmitting that data as end to end. In this instance, you can see the radio network is like working as a black box in a more modern type concept of very independent communication, where you basically it will provide a standardized Ethernet interface on the train, and on the other side in the depot where the service were terminated and basically was transmitting any data that the data stream was injected in the interface the network was presenting on the other hand. In terms of test execution, so you can see this is we have had more than 140 testing scenarios and 6 test drives. So you can see it's quite extensive and demanding, testing activity has been carried out. We covered the RF scanning, capacity testing, data stream testing, overload testing, degraded mode, where we switched off a specific radio unit to understand the change of the radio condition. We also tested macro handover between the macro and the radiating cable. As I said, we had the single train run and the 2 train runs where the second train was acting as a disturbance of the radio environment to understand in a real scenario where you have 2 trains running in parallel what is going to happen to the radio coverage. And of course, as I said, the test track is offering the possibility also to test the train at the maximum speed, that is 80 km/h. And all these tests has been carried out using a test run package, where a test run package has been defined as a combination of 4 test run. Basically, it was a westbound to eastbound. So running at full speed 80 km/h, and then going back 80 km/h in the other direction, then return at 20 km/h, stopping at specific location that were defined as part of the test plan strategy. In order to test specific condition, physical location, and specific condition where we want to test specific behavior of the network. Of course, this has been very demanding. We had 2 intense test weeks. We went there to Helsinki, and myself and Dimitri, we were there witnessing the test, participating in the troubleshooting. We had a number of issues we had to also to overcome, but also we had the chance to visit and familiarize with the network to support the client with now with the procurement phase we're going to discuss in a moment. So I think with this slide, I will hand over to Dimitris to continue on now the test results and the final conclusion of this pilot.
Right. Thank you very much, Giuseppe. It has indeed been very fun. It was very demanding. Those dark gray, I would say, November days. It has been very demanding, but very interesting, very innovative what we did. So on the next few slides, I'm going to try to condense what was a 200-page, very extensive result analysis document into a few slides only. So yeah, I can try and do that. You're going to tell me later if I made it. So this table, it might look complicated, but it's nothing more than just a checklist, essentially, of whether in the private 4G case we can meet the specific key performance indicators for the individual data streams. In this table is the train control data stream, the critical VoIP stream, and the train CCTV stream. If I may explain, the reason we have the north-south and combined view is that because there were some technical limitations from the routers used in the pilot, and it was not possible to set those up in an active and hot standby configuration, which would be more reflective of the actual intended system. So what we did, during each run, we were sending data streams through both routers, from the north side of the train and the south side of the train, and then the results were combined in a sense in order to present that bottom three rows of the north and south routers combined view. So that's what's happening in the private networks case. All in all, very, very high level observation. So the private network can comfortably and consistently fulfill the requirements for the ATC and critical voice. CCTV, so the CCTV streams for each router, they failed their key performance indicators, but this was purely because we have reached the uplink capacity limit of that channel. It was a 2300 megahertz frequency with a 10 megahertz bandwidth. So we had reached the 10 megabits capacity limit on that channel. If we had more capacity, we had more bandwidth from that channel, so the CCTV stream would be perfectly fine, even with the strict requirements that we put, which aimed for GOA4 operation. General observation about the private 4G. As I said, in the normal operation mode, the band used and the density of the radio units was demonstrated to fulfill the requirements for ATC and critical voice. During the degraded modes, which was when we were switching off certain radio units and testing what was the effect on the data streams under test, there was some service degradation that was observed, but this was mostly happening in areas where changes in radiating cable topology was occurring. For example, the radio cable was going under the track, joined with a long coaxial cable run to move from the middle of the track to the south side of the track, or when we were changing positions within the tunnel, so moving from the side of the tunnel to the top of the tunnel, which was expected, to be honest. In any case, in those areas, only uplink performance was affected, which again was expected because radio cables, for any radio engineers here, they are uplink limited systems, so it was expected. What was very interesting to notice, there was limited effect on the downlink, really. This was attributed to the private nature of the network. There was extremely quiet this band. This was dedicated for the city transport use. There was no interference whatsoever. So the system was performing very, very good in a very low signal scenarios, what other systems could consider as potential cell edge. Also, the two rooftop macro sites were able to provide good coverage and very good and fast handovers to the open track area when we were switching the radiating cable sites in the same area off. So that test was also successful. Next, the public 5G non-standalone. Essentially, non-standalone, it was requiring a 4G anchor. In a sense, this was the dominant network in Finland at the time that we were testing. Again, the same table, just a checklist, mind you. So, we had much more capacity there. The public network could serve essentially all the data streams that were simulating the different metro applications, including CCTV. Results could be fair. We were noting some kind of discrepancies in the continuity result, but still meeting all key performance indicators. They can be improved if certain radio parameters are fine-tuned in a full system deployment test scenario. The only failure, in a sense, was the Wi-Fi stream. It couldn't achieve. We could achieve up to, I think, 150 megabits stable rate on the stream that was simulating the public Wi-Fi. I provided a Wi-Fi connection for the entire train. The intended rate was 250 megabits. We couldn't achieve this because, we did some extra tests with the mobile network operators public network. We could achieve much more capacity than that. This can be further improved if the end-to-end connectivity is optimized. I'm going to come back to that a bit later. So, general observation about the radio environment as well. The signal quality and the signal levels were almost excellent throughout the tunnel during both the normal and during degraded mode scenario. So even when we were switching in-tunnel radios off, the signal was still very, very good, which shows that the radio design can actually be rationalized. Potentially, we don't need to have so dense cells. So the radio units located so close to each other, very useful for future potential deployment. There was some degraded signal quality in the open track area, though, when one of the tunnel radios was off. So this means the radio design needs to consider sufficient coverage is provided between the tunnel and the open track areas, the macro layer, in a full deployment scenario, and that's what I mean in the first bullet point. I say better located cells, so less density but better located. Maybe move that tunnel edge share closer to the tunnel edge. There were a few occurrences of a longer than average also delays, meeting the key performance indicators, but a few discrepancies there, longer than average delays in a certain handover area within the tunnel, which could be attributed to a number of reasons: geometry of the track, the size of the tunnel it was opening up in that particular location, and also don't forget that the directions that we had on the tunnel wall, they were actually lower than the roof of the train. So in that location, we could potentially raise those antennas. Potential problem solved. Now, the next set was the private 5G standalone. Again, I would like to draw your attention to the north and south sides combined. Again, just to remind you that we couldn't operate the routers in a hot and active standby configuration, which should be the case in the full system. Also, the 5G SA network implementation that we had on the test track during those weeks of testing, it was the first 5G standalone commercial network in Finland. It was in beta use, not yet accessible by the general public. I believe last month, the mobile network operator in Finland that we worked with, they launched this 5G standalone network for access to the general public. So it should really be done now. It's out of beta for the software people here. So in general, when we see both north and south sides combined, the 5G standalone private network can comfortably and consistently fulfill the requirements for ATC and critical voice communication. CCTV again would fail because we didn't change the fundamentals of the radio. It's still a 2300 megahertz frequency and a 10 megahertz bandwidth, so the capacity limit is there. It's law of physics, let's say. Now, the reason you see the failures, let's call to the consistent performance indicator for the individual routers, it was that they weren't able to maintain a stable communication path compared to the private 4G, but this was only happening when the radiating cable was on the other side of the train compared to the respective routers and antennas. Otherwise, so the router that was expected to work perfectly, it was actually working. We fully believe that the results can be further improved with improved maturity of the 5G standalone technology and actually field tested and tested by the supplier with the network operator standalone routers, which is the case now, actually. And saying that, I have to say that compared to 4G, anyway, we did notice a performance improvement in terms of both the data rates, the downlink data rates, and the latency of up to 40%, showing the superior efficiency of 5G standalone compared to 4G. Some overarching observations about all the tests now that we did. So both the private network, either 4G or 5G, and the public network are suitable to support the train control requirements. In high public network scenarios, quality of service, of course, should be implemented to ensure the reliability of any safety critical streams and make sure that any, for example, like a public Wi-Fi stream does not consume the entire bandwidth. It doesn't allow for safety critical streams to work. The public network could fulfill the role of the backup network for the ATC traffic in all areas. Also, the private network on the other side could fulfill the role of the backup network for the lower bandwidth only train service, again because of the lower bandwidth of that private network, the 10 megahertz. Also, number of hops between end device and mobile network operators should be optimized in order to achieve maximum capacity. This was the reason that we couldn't achieve the maximum capacity for the public 5G NSA, if you remember when I noticed it. So when we optimized the number of hops between the end device and mobile network operator course, the problem immediately went away. Very, very important, I will put my radio engineer hat on. For maximum redundancy, of course, the radio design should avoid by designing public and private or dual layer network cell edge areas at the same location. The network design need to be overlapped in order to maximize reliability of any dual layer network. Also, we will need to have routers or mobile gateways, however suppliers want to call those days, working in a high availability mode, or potentially application device that can manage packet duplication via multiple routers. This is also another method, to increase the data communication reliability. Now, but because we weren't so very, very busy, of course, with doing all this about the pilot, we also, at the same time, we did several market engagement exercises, 3 rounds of market engagement exercises, actually in the form of RFI questionnaires. The first round was carried out in the summer of 2022, just actually a year ago, exactly a year ago. This was directed to signaling to train control system suppliers that had a dual aim. First of all, to establish the market's view, of course, on the requirements that an ATC system would have on the radio communication network. And this fed the table that this fed, part of this fed into the table that Giuseppe showed at the start. And also to check each supplier's thoughts on the underlying technology, cellular, Wi-Fi, wireless mesh, combination, or in terms of risk, cost, and potential future proofing. Then in the autumn of 2022, we ran a second round of RFIs, which was targeted to organizations capable of delivering track-to-train radio communication systems. Anyone. So this could include the traditional ATC suppliers, mobile network operators, solution providers, private network operator events. The aim was dual-fold, essentially to get the market's view on a series of technical and procurement questions, whether there are any showstoppers in their minds about either technology-related or procurement contractual related that potentially could prohibit them from implementing their own proposed solution. And then after the pilot was concluded and we discuss the results with City Transport. We did the third round, the final round of RFIs. It was a couple of months ago, really. So this third round was targeted to the same organization as before, so anyone who can provide a track-train radio communication system. And we sought estimates on the budgeted cost and the schedule, thinking about the new radio network. As you can appreciate, we are not at liberty to disclose any of those results of what was or what we learned from those RFIs. I can say that none of that actually surprised us, so it was pretty much expected. But we can say that even amongst the traditional signaling suppliers, there was a consensus that cellular mobile radio is the way forward. So, pilot results, RFI findings, and also combined with our views of the current infrastructure within Helsinki Metro, led us to our final recommendations and conclusions. We came up with a list of key decision indicators. This is a truncated list. This is not everything. This is what we are able to show. We came in agreement with this list with our client, with the Helsinki City Transport. We presented a checklist or a tabulated visual summary, as I like to call it, of how each technology or each layer within a technology, a combination of players, is suitable against each individual key decision indicators. For the purpose of this webinar, we are just presenting here the cellular combinations for dual layer network, either two private layers, a private and a public layer, or a public and a public layer, as you can probably understand from my dual layer. So it was decided that the dual layer mobile network would be the most suitable to meet City Transport's technical and deployment requirements, as well as being the most cost-effective and future-proof solution, which still keep maintaining high availability. It was decided that this dual lane network will be acquired primarily for train control use, and the rest of the systems will transition onto it in the near future. Also, importantly, City Transport accepted our recommendation to not specify how duplication will be implemented in that network. We're going to let the market come up with the best cost-effective solution. So they come back with any kind public-private, or a private type of layer. What are the next steps? Of course, we have a lot of work ahead of us. We're going to be supporting Helsinki City Transport procurement through the next stage of the capacity upgrade program. We're going to be specifying, procuring, and evaluating a new radio communication network, whilst we ensure that it's suitable for the metro system of the future. Very, very important for Helsinki, one of the most innovative capitals in the world. And also, we're going to need to, of course, to be coordinating between all the different interface projects, namely those three: the automatic train control, the radio, the project we're talking about now, and also the computer-based interlocking. We have also developed a technical white paper which has been published by our client. I believe that we have agreed with Kaylee that once she shares the slides or the link or the recording of this, she's going to share a link to that white paper, which includes a bit more detail, not a bit, actually a lot more detail of of what we have actually presented now. And yeah, I think that was it. Thank you very much for attending.